Let's get to start today's class. Today's class, I will also explain about linear transformation. And in the last class, I gave what is linear transformation. It is a map from vector space to vector space, and some special linear transformation. Some special transformation is called the matrix transformation. It is written like Rn to, it is a map from Rn to Rm, and it is vector x goes to a matrix product vector x as the form column vector. So this form, if the linear transformation can be written like this form, then we will say it is matrix transformation, and it has linearity. So usually we say that this transformation to linear transformation, and I will give some examples. First, maybe I give this example in the last class. I will give one more. If the linear transformation is defined like this, then we might think this matrix as a matrix multiplication of this matrix A and vectors x1, x2. So it will be written like this form, and if you substitute another vector to x1, x2 vector, then this transformation will goes to 2 plus 4, 1 minus 12, minus 1 plus 4. So its vector is 6 minus 11, 3. And if you calculate this matrix by substituting to the vector x to 1, 4, then the matrix multiplication is also will have same value. This is same to this, and this product this is same to this, and this product this is same to this. So it will have same result. It is, so we might say this is representation of the linear transformation T. And I will give this linear transformation is very related to geometrical information. So I will explain some geometrical linear transformation. It is called reflect and projection, reflection, and rotation. I will explain rotation more a lot. Reflection is, you might think some similar to mirror if the in the space if there is point x, point y, and if you reflect this for the line x-axis, then it will be pointed to x minus y for every point in R2 plane. So the transformation can be written, its transformation will be operator because it will be send same vector space. So if you choose, I will write it vector form xy, then it will be x minus y. And if you calculate input the standard basis 1, 0, and 0, 1 to xy vector, then it will be goes to 1, 0, and 0 minus 1. It is t1, 0, and this is t0, 1. Then this is a kind of representation, matrix representation of this linear transformation. So from this, we might write this matrix transformation by using matrix like this, and it will give us the same result we want to reflect. So this matrix means reflection, and it has a similar quite special form because it is diagonal matrix, and its diagonal entry is 1 or minus 1, and all I think if you study the change of coordinate, then it has only 1 or minus 1 diagonal matrix for a basis, for a special basis. However, we didn't study coordinate change yet, so I will say just if you get the base, if you choose the base well, then you might represent matrix. You might get matrix representation, diagonal matrix. So reflection case, we see just R2 space. However, if we see Rn space, if you see an operator over Rn, then it also, if it was reflection, then it also will be written the diagonal matrix 1, 1 minus 1, 1 like this form. So if you see just matrix, then you can check the geometrical information. It will be reflected to the line X if you choose the standard basis. And of course, there are another linear transformation having some geometrical sense. Actually, almost every linear transformation has the geometrical information. I will give 3 kinds of geometrical matrix. And the second is projection operator, and the operator is, I will give the example on R2 plane, and if you have x, y vector, and the point is this point. And projection means it will be load some data in the plane. So if you project the point to x, then it has the coordinate x comma y, and it will be lost the y information. So the projection of x comma y will be x comma 0 if you project to x-axis. So I will explain the map. Then it will be go to x comma 0, and if we find the matrix representation of this, then we will input 0 1 and 1 0. Then the t10 will be same vector, goes to same vector, and t01 will go to 0 0 because the second second value is 0. So if you input 0 1 to the linear transformation, then it will give you 0 vector. So from this we can find the matrix representation 1 0 0 0 of xy vector, and it is also, I think, a special form because it is also diagonal, similar to reflection, and actually it has 0 diagonal entries. It is a little different from reflection. Reflection was -1. However, it has a similar sign because if you choose as the factor, if you choose Rn to Rn operator, and it is projection, then the matrix representation will be written 1 0 1 1 0 like this form. It is just different from -1 and 0. If you choose the basis well. And let me introduce the rotation, and it is fairly special than other linear transformation, reflection, and projection, because it was very easy to find the reflection and projection. And actually, although I give the simple example, however, if you want to see some other reflection or projection, reflection, then if you learn what is change of coordinate, then you, by finding the vector the axis vector, then you might get the matrix representation of the reflection quite easily. However, rotation is a similar, very special, and I will draw in on our plane. Okay. If you choose one point of this, I will start 0.1. Its rotation will rotate of counterclockwise, and if you move this point theta angle, then its point will be cosine theta and sine theta. So its linear transformation is if you input 0, of course we need to input x, y vector because we should consider all points. However, if you choose this point, it doesn't change because it will be moved of this form. And by choosing the two triangular, and you can get the sign. How we can express this point? It is a little. Maybe you are learned how to get this point by using the formula of addition. If sine theta plus theta is sine theta, cosine theta, and cosine B, and B. By using this formula, we can get the theta, and this point is theta, and this point is B. Then you might get the solution. Cosine theta, sine B, sine B, cosine theta, sine theta, cosine B. By using this, you can express this point. It is a little hard, so I will use. Finally, we will input the standard basis, so we will see. We'll go to the standard basis. 1.0 will go to cosine theta, sine theta, and 0.1 point will go to. I will get more higher point. If we choose theta, then it will go cosine theta minus sine theta. So it goes to minus sine theta. Okay, hello. And cosine theta. So by choosing these two, by using this matrix, we will find the matrix representation. Then the T of xy is T of 10. It is cosine theta, sine theta, and T of 10 is minus sine theta, cosine theta. And we will input the vector x, y. Then, if we find just from standard basis where they to go, then we can find for any vectors in R2. For example, if you get this point was cosine phi and sine phi, this length was r, then if you input the linear transformation t, r cosine phi, r sine phi, then it will be given the same solution. You just draw two triangles, and you by calculating the sine cosine formula, and then you might get the solution. However, if you use this linear transformation, the matrix representation of linear transformation, then you might get more easily. You might get easier than just calculating by triangular. R cosine B, R sine B, and then R cosine 0 cosine B minus R sine 0 R sine sine B. By calculating another, R cosine 0 cosine B. Oh wait, I calculated. It is just 2 by 1 matrix because we input vector. Sorry, and R sine zeta cosine B, then plus R cosine 0 sine B, and then it will be written cosine 0 cosine B minus sine 0 sine B, so it is cosine theta plus B, and sine cosine cosine sine, then it is sine 0 plus B. So it is just will make the axis plus, and actually if you calculate this, then you might get the solution of cosine 0 plus B, sine 0 plus B. And actually rotation, these three geometrical linear transformation is very special, because if you choose two reflection, then if you reflected from x first and y-axis secondly for point A, B, then it will be go to A, minus B, and minus A, minus B by the reflection of y. And however, if we calculate it, y-axis reflection of y-axis is first, and the reflection by x is secondly, we calculate reflection x, then it will be goes to minus A, B. Finally, it will go to minus A, minus B. Then it means the matrix transformation, we might consider the double matrix reflection. I will write, if you made reflection by axis A, then I will write this form. Y x is equal to x y, and we learned the matrix representation, and the y the reflection by y axis matrix representation is minus 1 0 0 1, and it is reflected by x, and we find this reflection, and the right term is 1 0 minus 1 and minus 1 0 0 1. It actually minus 1 0 0 minus 1, and it is also reflection by the axis y and y equal minus x, and it is means the y equal minus x-axis is reflection. And actually, we learned matrix cannot be generally cannot be commute. However, the reflection, we saw that reflection has commute property. And actually, if you consider the projection with projection, like if you okay, in R3 space, if you choose A, B, C, then you can choose the projection to XY plane. Then it will be go to B, C, and by choosing projection to x-axis, then it will, oh, wait, oh, I misread. AV0, and it will be go to A00. And it is also commute because if you choose z-axis first, and then this point is A0C, and by choosing the projection to x-axis, then it will be go to the same point A, 0, 0. So the project for each projection also has commutativity, and rotation also we can solve the situation. If you use from this form, then it will be move this and this rotation by the angle theta and b, then it will be moved to theta plus b. So we write of this form to the rotation, and if you calculate sin 0, sin 0, 0, matrix multiplication, cosine b minus sin b, sin b, cosine b, then you might be able to use the formula of summation or subtraction of triangle function. Then you might get the solution. This sine plus b, and that there is a student of my TA class, and actually I give this question, this problem to the homework, so you might get the this problem. You might calculate this problem in the class, today's class maybe, and it gives very good geometrical sense, and I think it this matrix transformation used in many kind of industry, like if you consider the consider a game, then the character will be moved, and why we can move the character well, then it is used this matrix transformation to the code. Of course, there are another example where we use linear transformation is when when some pilot will will drive their plane, and then the airplane or jet plane will be need to rotation or will be moved, and we might want to the position of plane to move well, because we should calculate the axis or to go to the proper position, because the reason why we use plane is for move to another place or some to bite as jet plane case. So it can be used. The linear transformation can be used a lot of situation in real world. Actually, I have ever the computer a little higher technology. It was hologram, and it was dragon, and actually it looks very good, very well, and the dragon was also moved a lot in the stadium, and this hologram is also will be used this linear transformation, because it is not real object, and to move in real world, then it is used to move well, then we will code by using this linear transformation. And here I will explain a little more about rotation. And rotation, we see just R2 plane rotation, and I explained rotation is quite difficult to find the matrix representation. So actually, if you consider R3 to R3, then it might be hard to find the all rotation. I skipped the 2x2 on two real plane, then its all rotation can be written the form cosine theta, sine theta. It should be written like this form. However, in R3 space, it might be hard to find this form, and actually if I give the answer, then it usually written B theta triple or B theta psi, and by using the method I will write. It is a linear transformation, and we considering the projection with rotation with projection, then the rotation will be the rotation on R3 space. If you project to plane, XY plane or Z plane, then it is Z axis. If I choose the rotation of Z axis and rotation of Y axis, and again we will use Z axis G. So I use the G for I use the G function. So it was rotation, so it might be written 0, 0, 1, 0, 0, because if we input 0, 0, 1 vector to the rotational z-axis, then it will not be moved if the vector on the z-axis. By rotating the z-axis, it doesn't move. Actually, it is same to projection and similar to projection, and we will write 1. And L zeta was the rotation by the axis y, and then its y-axis will not be moved, and another point will move just rotation of xz plane. So it can be written like this form. And finally, cosine psi minus sin psi, sin psi, cosine psi, 0, 0, 1, 0, 0. Then I will explain this linear transformation like this. I say the first we will move the z-axis. We will use rotation of z-axis. Then if you consider the sphere, unit sphere, then it has north points, and the north point and south point doesn't move by the z-axis rotation. And so if you choose first north point, then the second and third rotation will move another place, because if you turn the y-axis, then the north point will move another place. Then after it is moved by y-axis, then it will be moved by z-axis to another place, and all rotation will move the axis where the moved this all sphere. On all sphere, it is rotation on sphere. Then by finding the point to this, and this means the second and third rotation, and also if you use just two linear transformation, then you will find just this moving this point. Of course, when move this, another point will move the same position, like this linear transformation, this rotation. So it doesn't move this way. So we need the rotation of by the axis we found, and that rotation is same to the first rotation. If you first rotate by axis z, then after then, if you move to the axis, then we will get the rotation by this axis. So by adding the z-axis rotation, we can get the all rotation on R3 plane. And there are many illustrations for this rotation. And if you okay. There is a mic issue. So by using projection, and rotation, you might express more higher dimensional rotation also, and it will be used in real world. And actually, usually we will use the rotation in R3 space because we live in three-dimensional world. When I explain the the rotation on R3 plane, I written the composition of matrix linear transformation. The next chapter is in next chapter we will discuss about composition of matrix transformation. And I think you can imagine what is this. It is same to just composition of function because I explained the transformation is same to function, and it just is domain and codomain comes from vector space. So it can be it has the linear linear transformation also has composition. If we give the two linear transformation, one is from Rn to Rk. Of course, the codomain space and domain space should be same. And the second matrix the linear transformation from R to the k to R to the m. Then we might consider the function composition Tb composite Ta from Rn to Rm by Ta Tb, and we we represented this for each linear transformation to the matrix A and matrix B by multiplying this matrix of left side. So if you give vector form, then this will go to A x1 to xn, and it will be go to B A x1 to xn, and matrix multiplication have the property of associativity, so it can be written the matrix multiplication BA to the vector x. So this matrix this matrix representation comes from TBA linear transformation. So the matrix transformations composition can be written the matrix multiplication. It might be a kind of why we calculate column and row when we multiplicate the matrix, it is very useful because it made associative rules. So next, I give some example, and if you want to more example, then please read my lecture notes. I will give one example for the explanation of commute. Example. The T1 from R3 to R2 and T2, we define two linear transformation. R2 go to R3, and then and we will define this from x, y, z point to x plus 2y, x plus 2z minus y. Then its matrix representation will be written by T100, T010, and T001. So if you calculate it, then you might get 1, 2, 0, 1, 2, 1, minus 1, 2. And if I define the second linear transformation, if you input x, y, it goes to 3x plus y, x minus 2y. Then this matrix, for this linear transformation, if we find the matrix representation, then it will be 3, 1, 1, 0, 1 minus 2. And then by using this matrix, you can calculate T2 composition T1 or T1 composition T2. And I will give it is exercise as an exercise. This matrix will move from R3 to R2 to R3, and if you give x vector, I will put in vector form x1, x2, x3. Then by the first linear transformation, it goes to x1, x2, x3. And if we calculate it, x1 plus x2, x2, x1 minus x2 plus 2x3. Actually, it is same to this linear transformation. And finally, we will move the two-dimensional vector by the matrix transformation T2. 3, 1, 1, 0, 1, 2, x1 plus 2x2, x1 minus x2 plus 2x3. Then it will be 3x1 plus 1, 4x1, and 2 products to 6 minus 1, 5 x2, and finally 2x3. Then the second coordinate is x1 plus 2x2, and the final coordinate is minus x1, 2 minus 2, 0, and 0 minus 4 minus 4 x is 3. It is same to the matrix. If we represent by using matrix, then it will be the 3 by 3 matrix minus 1 0 minus 4 x1 x2 x3 by using coordinate matrix, coefficient matrix, and by calculating I will use this space. By calculating the matrix multiplication on 1 2 minus 1 0 2 3 1 1. Oh, I cannot input the video. If you calculate it, then 3 plus 2. Oh, wait, why it is different? X plus 2x 2 and 1 minus x2 plus 2x3. Why is it different? I will. Yeah, it should be 4, and I miscalculate because it is T1 composition T2. We calculate T2 composition T1, so the result was different. I will calculate again. 3 1 1 1 0 minus 2 1 2 0 1 minus 1 0. If we calculate it, then 3 plus 1 4, and the second row and 6 minus 2 4 4 6 minus 1 5 and 0. The second row was 1 2 0, and the final row will be minus 1 minus 4 not minus 4 0. Is it right? The last one, 2 plus 2 plus 4. What? It was 2. Sorry. And then the we will calculate the final line again. 2 0 minus 4. Oh, why is it different? I'm not good at calculating. 2 plus 2. Did I mistake? So 4 5 2 1 2 0 minus 1. I think I miscalculate on this point. It was the final line, and the final equation of 2. Then 2 plus 2 out. It was 4x2. Okay, I miscalculate because if we calculate it, then we get 4x2. So we can see that the matrix is same, and if you calculate T1 composition T2, then it will be give the 2 by 2 matrix, because it will be moved R2 to R to the 3, R to the 3 to R to the 2, so it will give 2 by 2 matrix, and it is same the if I denote A and matrix B, then A matrix multiplication B. So actually, if you can, as you can see, it is different A multiplication B and B multiplication A. It is different. Its size is also different. So generally, if you consider two linear transformation, it doesn't commute. So I say the three geometrical linear transformation are special. It has commutative for themselves. And next, we learned the inverse matrix, and actually it will give the inverse function if it can be inverse. If it has inverse matrix, the matrix, that means the matrix A is invertible. Then the matrix, the inverse function of the linear transformation will be T A minus A inverse. So that means if the the matrix representation can be inverse, then the function is also, the matrix transformation is also invertible. It has inverse function. And it is quite simple if you consider Rn to Rm. It should go to same dimension because the condition of invertible, we have square matrix, so the TA linear transformation is operator, and by giving the vector x1 to xn, we will calculate it by multiplying A. And if we written this is W1 to Wn, then we might get the inverse function of TA, Rn to Rn, W1, Wn. We get the vector from Rn space, then it will be give this linear transformation, and that means the linear transformation comes from A inverse matrix. And if we consider the composition inverse, then it will be give A inverse, and it is identity matrix, and so it means is identity linear transformation. Because the matrix will be give x1 to xn goes to x1 to xn. So it is same to identity matrix, identity linear transformation. So we might get the I write this TA inverse and TA inverse. It is same TA inverse because we get identity matrix. And if the function is invertible, so have the inverse function, and if you compose the inverse function, then it will be identity map. Conversely, it also makes sense. What time is it now? Okay. I will enter the next chapter also then. It is not related to our class. I like the linear transformation because it gives geometrical sense also by using algebraical concept. And maybe many students will have heard from linear transformation, and I used just Rn space. However, linear transformation can be used all of vector space on vector space. So we sometimes use the space of polynomial having less than or equal to degree t over R or over C or over Q, and also it is also vector space, and actually it is quite different because it has infinitely many dimensions. However, all polynomial is I will written px1. Then it is also a kind of vector space, and so we can, by using linear transformation and by using algebraic sense, we can study for matrix transformation. So although I give the very simple example, and however it is very hard point in mathematics. From this, we finished the chapter 1, and the amount of introduction points of this in Howard Anton textbook, there are many pages in chapter 1, so I used lots of time to explain what is matrix and linear transformation. Next chapter is determinants, and actually before the new students come to this class, I explained a little for determinants. On 2x2 matrix, if you have, I will give A, B, C, D notation. B, C, D, and its determinant is a function to, it is real valued function. So it will be give the real value AD minus BC on 2 by 2 matrix. And I explained if it is non-zero, that means the matrix A is invertible. And we just study on 2 by 2 matrix. However, by expansion to more higher dimensional matrix, we want to get invertibility from the function, real valued function determinant. Of course, there are other contents in determinants. However, in this book, we will use determinant by finding the invertibility and inverse matrix. Let's consider the matrix A. I will write one more. If A is A, B, C, D, the determinant of A is defined AB minus BC, and it is denoted determinant A is, because it is a kind of function, so sometimes write determinant of A is AD minus BC, or by using the absolute value of matrix. I don't know if it is right expression. We will write AD minus BC. It is just notation, and I will recall one thing. For 2 by 2 matrix A, if its matrix is invertible, then the inverse matrix is 1 over determinant of A, D minus B minus C, A. We calculate it, and we will focus why it is pointed this, and from this we will expansion to higher dimension of matrix. And then we will start from 1 by 1 matrix and define the determinant of 1 by 1 matrix. A11. I will write the notation where there is row, first row and first column. Then I will write A11, and its determinant is just A11, and it is it's okay. And we, from this, we might think this point is for dividing the matrix for each vector. Actually, by choosing the first vector, we choose these points, and we 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 get the D when we as the inverse matrix, and it is remove the first row and first column, and if you see the second column, then it is I mistake. It is not this point. So if we choose A, then the remaining matrix is 1 by 1 matrix, and determinant D, it is reduced matrix of this whole matrix, and by calculating alternating sum, or by choosing another point B, and its remain matrix is C. So we can analysis about the determinant map is expanded by lower dimension of matrix. I will to construct this process, I will give the next definition. We defined the determinant in square matrix, so we will expand to square matrix. And so if A is, let A be a square matrix, then we will say the matrix, another matrix is minor. So the minor of entries of we choose the one entries in matrix. The entries will write Aij is i's column, and it has i's column and j's i's row and j's column is denoted to be the determinant of another matrix. And in the first class I said by dividing the matrix, and divided matrix is called it submatrix. So I will use the notation the word submatrix. The matrix that remains after the i's row, j's column removed or deleted. From A. So the minor and the minor is if we consider 3 by 3 matrix, then we might be able to choose on entries A to 1, then it will be removed, it will be delete I row and j's column, and then the submatrix will be A12, A13, A32, A33, and its its determinants will be minor. So the determinant of this matrix is minor of A to 1. of A in A. And also we need to the name of what we choose. So I will define the number of we did alternating sum, so the number i's row and j's column entries. I will write notation aij is denoted sometimes it denoted by Cij, and then it will be written Cij determines the minor matrix. I will this minor matrix remove the I and j matrix. So it will be a coefficient of linear combination. So sometimes it usually it is denoted C by using C, and it is called the cofactor of entry AJ. Aij. So as the example, let me calculate the determinant of 3 by 3 matrix. Not calculating. We didn't learn the expansion to determinants. We just get the 1 times of expansion. So I just explain the notation. Let A be a matrix 3, 1 minus 4, 2, 5, 6, 1, 4, 8. For this matrix, if we choose second row and second column, then it's minor. If we find the minor matrix, minor of entry 8 to 2 and 4, 5, then its minor is determinants of the 2 by 2 matrix. And we know the 2 by 2 matrix determinant, so it will be 3 times 8 minus 4 times 1. So 4 minus 28. And we called this entry 5 is cofactor. It is called the cofactor. And finally, by making the linear combination of these choosing, and actually we will choose column or row finally as to find the determinant, because when we calculate the determinant of 2 by 2 matrix, we choose the A and next we choose the B. We selected the column vector, and by choosing it is row vector. By choosing column vector, we also can be can be given the results like determinants D, alternating sum, and C, determinants. If we choose C, then the remaining matrix, submatrix is B. So it is also AD, same AD minus CB, and is commute. So we know it is same. The determinant we know. So actually, it might be needed the proof why it is same in all matrix by choosing any column or any rows. However, it is very makes sense because we will choose the minor matrix to make one by one matrix. Then finally, if there is some entries, then if you consider the first entries, then its minor matrix will be 3 by 3 matrix, and by choosing another entries, then finally we couldn't choose the same column or same row again, and finally we will get the one by one submatrix of the matrix. Actually, by choosing the column, then it means all kind of sets we choose the 4 entries first, and the next we will, if we choose, I will use another color. If we choose these entries, and then there are factorial kinds of choosing points because this case is for factorials, because if we choose one among the 4 entries, and then next we will get 3 by 3 matrix, then we will choose 1 entries on 3 by 3 entries, 3 column entries or row entries, and next we will choose 2. Finally, we will get 1. So we get the 2 find determinants. We will calculate all kind of choosing in this matrix. So it doesn't depend on the choosing from column or row for each color for each row. That means it gives the results of theorem. So let A be a n by n matrix. Then regardless of column or of which row or column of A is chosen, we obtain same determinant always. So then by choosing some row or some column, we can calculate the determinant. So I will calculate again. I will choose the second row, and firstly I choose the entry 5, and the minor matrix was the minor was 28. Then each point is +1, -1, +1, so it is alternating. It can be alternating. So 1, -1 plus 2 plus the second row and second column, and the cofactor 5, the determinant of minor matrix is 28. And also I choose the second row, then we have the first entry of second row is 2, and it is the second row and first column, and the cofactor is 2, and the minor matrix is, when we choose 2, the minor matrix is 1 minus 4, 4, 8, and if we calculate the determinants, then 8 plus 16, 24. 24. It's 8. Okay. And we will choose the binary entries of the row 6. Its row is second row, and it is third column. And the minor matrix is 3, 1, 1, 4. The minor is 11. So the cofactor was 6, and the minor is 11, and we summation 3 and 3 numbers, then 140 minus 48 minus 66, then 26. Is it right? Maybe. And 40 minus 8 minus 6. Okay. So the matrix, for the matrix A, we can get the determinants for 3 by 3 matrix A also, and we can expansion to higher dimension also by choosing all choice, by choosing column or row, and it doesn't depend on the where we choosing the row or column, because it is all kind of selection. And sometimes I said it is written that form, so finally if I present the linear combination form, the determinants of A for n by n matrix A, it will be C. I will write cofactor first. Wait. What do you write? Oh, okay. I will write cofactor and the minor. I choose the first, the j's row, j's column, then first row of j's column and second rows of j's column, and it will be calculated nth column and nth row of j's column value. And this theorem means it is same if we choose ith row, then it will be give I1 cofactor, I2 cofactor, IN products cofactor IN. So it is a kind of linear combination, and determinant is also written like this. And actually, since it doesn't depend on the choosing of column or any column or row, so we can say determinant, the function determinant is well defined. I prepared on like this, so let's finish.